And the duration of the talk is 12 minutes, and we will have 3 minutes for possible questions. I will keep the time and inform you. So the first speaker is Vasilios Vasios from Brussels, and he will talk about labyrinth. I have to say that I'm not very far from the true labyrinth. Okay, I'm just a few kilometers away, so I have to comment on that. Labyrinth chaos and labyrinth walks, elegant chaos and chaotic walks without attractors. Okay, Vasily.
Hello, everybody. Nice to be seeing you all, or half of you. Anyway, this is a paper that has been put forth due to by these happy authors, which one is Anos Alatifi from the University of Qom at Iran, Persia. The other one is an old friend of Antonopoulos, who is now at the university, professor of the University of Essex, and me in Brussels. And this presentation came up because we all have been influenced, and we all have been somehow students of Ressler, whose birthday we are celebrating this year. It was supposed to be a normal conference, but it became a Zoom birthday celebration. So it was the first time in my life I saw Zoom birthday cake and celebrating the great contributions of this great man. So there's a focus issue. You can find this. You can find the preprint of the whole, whatever I say, because it will be necessarily very, very fast. But all the details, all the equation, it's a mini review. So it's written for people who are not really into this kind of esoteric but not obscure part of dynamics, because it's a kind of fundamental issue, the issue of feedback circuits, cycle, the logic and topology of chaos was a prominent discussion with most of the founders of chaos theory, like René Thomas, Otto Ressler, Grégoire Nicolas, and Leonid Sinigov. They wanted to find what is the necessary condition of chaos. And labyrinth chaos was discovered by René Thomas and Otto Ressler in a creative play, but not necessarily for just fun. It was very great fun, but and I could see them play, but it was very, very much into the heart of chaos. What they proposed was a paradigmatic class of continuous flow dynamical systems in a modular connection. So you have a set of differential equations which one variable influences the other in a cyclic motion. So it's a feedback circuit, and feedback circuits which are essential in the idea of inter complex dynamics. We all know that from circuits that we are using, feedback circuits that control homeostasis, or positive feedback circuits which control growth. For example, when a fruit ripes, it gives out ethylene. It's produced by another fruit. The other fruit gets ethylene, getting ripening also faster, and the whole tree follows. We can also have in engineering, apart from physics, biology, in engineering, you can have also mechanisms where you can switch from negative to positive feedback. So if someone tells you to slow down, you can either push and go fast, or you can really brake depending on your desire. So what is clear for this study of the logic and circuit in dynamical systems is that a positive circuit is necessary for the system to have stable states. A negative circuit is necessary for the system to exhibit sustained oscillations. And what Thomas and Ressler discovered by playing with these models and paradigmatic dynamical systems back in the 90s is that the necessary condition of chaos is the presence of both a positive and negative circuit. This is a necessary condition, not the sufficient condition, but still it has been developed by graph theorists and people in abstract mathematics to a great extent. So the feedback here is when two variables in the Jacobian are connected. So if you write down the flow in the Jacobian, each part of the Jacobian is a negative or positive feedback circuit depending on the value of this entry of the Jacobian. Here you see the labyrinth chaos, and here you see the Jacobian and the circuit that comes out from the Jacobian. Now you see some self-referential circuits, which are the diagonal elements, and this is the dissipative part of the flow. And you can always treat that dynamical system with the tools of Lyapunov exponents, etc. You see that there are some chaotic regions and some other which are not chaotic. In B equals 0, it's a very interesting region, and that will be shown in a while. This is a typical figure of coexisting attractors for B equals 0.18 or something. And it's a zoo of coexisting attractors, of periodic orbits, of all kinds of, all the repertoire of complex dynamics. Even 6 coexisting attractors can be found. So the labyrinth walk is when you the dissipation disappears. We put B equals 0, the diagonal elements disappear from here. And the picture that we get is very strange and very interesting. There are no chaotic attractors, but there is chaos. And this exemplifies what I'm saying. You have the initial conditions very close to each other, one red, one blue. The red goes this way, the blue goes this way. We are at B equals 0. But where is the attractor? There's no attractor. A labyrinth walk is a chaotic system. It is conservative. There's no attractors, and there are infinite unstable fixed points in the state space. Looks like that. An infinite lattice, three-dimensional, with unstable points, with very great nice symmetries. Each part of that has eigenvalue, complex eigenvectors and eigenvalues, the roots of unity, in a very nice, intricate symmetry that we cannot go through that here. So, but the interesting thing, more interesting thing than that, for some people who are dealing with physics, is that they describe, they show a fractional diversion motion as in a stochastic system, although the whole system is deterministic. I don't know any other system that can do that, but maybe I'm wrong. The labyrinth walks is volume preserving, obviously, since the diagonal elements of Jacobian are 0. So by Liouville equation, we can write down, we can set for Hamiltonian, but if we do that, and we follow 2 different paths from this vector potential that one can find, we see that the system is not first conservative because this path and this path are not at all the same, they don't give the same force. So the force is not, the system is not force conservative. Another peculiarity of the system. If we can push this envelope and we go for looking for a symbiotic structure in the 6 space, which means velocities and positions in the standard Hamiltonian formalism, we see that there is no constant of motion. And it's obvious it's not constant of motion because if there was one, then there would be no chaos. But we have chaos. So the system does not admit any global emphasis on global constants of motion. Could we look for a local constant of motion? Of course, there is a standard technique where one can apply, and we did that in the paper. Then there is a requirement that cannot be satisfied. So we conclude for the moment, because there are many things that we have to go and discover in the future, that our system is chaotic, labyrinth walks. There are no stable periodic orbits. There are only unstable infinite fixed points in its phase space, no attractor. It is conservative in the sense of Liouville. It has no constant of motion, even locally, and it's not force conservative, as there is no scalar potential. And it's not Hamiltonian in the classical standard sense. Could it be Hamiltonian with a vector potential? It turns out, and this is the subject of our next investigation, that there is a vector potential. Very interesting and very symmetrical, actually, and or which will give us a Hamiltonian with constraints. So the system can be forced to be Hamiltonian if we have Hamiltonian with constraints, but it's not standard Hamiltonian with force conservative structure. Another interesting thing is Chris is fascinated with chimeras, and he put already these systems in in a setting of a network, standard network that have been people have been studying in chimeras, and a very linear feedback between these things, these variables, and some of them are connected by depending on how much you want to choose. We choose half and half, and we play with only one parameter because there's only one parameter except the coupling. And we decided to play to put one chaotic walk and another quite chaotic labyrinth walk, and the other one labyrinth chaos. And the result was astonishing because we found a persistent ability of creating chimeras, even if you have labyrinth chaos and labyrinth walks. Okay, if it's chaotic, the system, we know that it has been, they have chimeras, and all these kind of systems are very, very easily to show that you have this chimera-like ability. But usually they are coupled systems with attractors like Lorentz or Ressler or whatever. But here we have a system which is half without any attractors. Brownian motion diffuses the system, and yet it organizes the chaos on the other side. So when I come to wonder about this system that the genius of Ressler and René Thomas have created, is like a platypus. Platypus is a thing which is a being, an animal, which was discovered in New Zealand, and nobody would believe that this is a real animal. It's like a duck. It lays eggs, but it's a mammal, so it nourishes his little children suckling. So it's in between everything. This is exactly what we feel with this system. It is very elegant, it's conservative, path dependent, non-Hamiltonian chaos without any attractors. Already you have a lot of things that they seem contradictory in terms. It has a very placid and very plastic ability of chimera-like states. It admits a vector potential which gives you a big hint about active information transfer, as has been proposed by Healy and Bohm in their theories of quantum potential and vector-like vector potential information transfer. And of course, it is related with other models of the same symmetry or similar symmetry, which are in the literature like ABC turbulence and Lattice-Lotera variants, and a very, very similar system which is called Ikeda delayed differential equation. And all this is, if we play with the symmetries and symbolic dynamics, which is something that we want to do in the near future, there are points to ponder. So the genius of Ressler, although if he reached 80s, he's still active on that. And with that, I would like to conclude.
Okay, thank you very much.
Thank you.
Thank you very much, and also thank you very much for being on time. Is there any question? Is there any question?
It was
Okay,
very clear. Everybody understood everything. Fine.
Well, I have several questions. First of all, I find this very interesting. I have never heard of this before. And now, in the simplest case, that if I understand correctly, you have the dynamics of one variable is controlled by like this. Okay, so the x1 dot is equal to sine of x2, etc.
Yes.
Now, how realistic is this system? That is, if we say that this is, let's say, over dump dynamics and we don't have a second derivative, that's just for the sake of the argument. So it's like having the dynamics of one particle being controlled by something, by the directly from another particle. It's like the there's only interactive terms to say. Okay, do you have a sort of a model for a simple model where this would apply?
Yes and no. What I'm trying to say is that this is not really something that can be applied directly. It gives the idea and some insight into the fundamental working of the formation of attractors or not. these systems are coming from biology mostly. They are inspired from biology. That's why I said Lothar Volterra, where there's no dissipative term. And also the Ikeda kind of models are applied in neurophysiology, the delayed. So it's not really something that you can apply now or in the very, very near future, like in 6 months. Although it has a very deep connection with the hypercycle model of Eigen.
Ah, I see.
So, I mean, yes, so this structure has been proposed by, this structure has been proposed by Eigen as a fundamental cycle that drives evolution. It's a very strong proposal, but it has. If I want to connect it with something, I would connect it with biological models.
Okay, all right, fair enough. Okay,
but no, it's pure. It's not applied, but not useless.
no, I didn't use this word. I find this quite exciting, but you know, trying to always, if you have some specific application, a very simplistic model in your mind, then it helps. That's why I'm asking.
Sure,
okay.
Yeah.
Okay, thank you very much, Vasily, and we go to the second speaker of this session. Hello, Melvin. Melvin Tailu.
Yeah, that's it. Hi, nice to see you.
Hi, Melvin. Where are you calling from? Where are you from?
From Switzerland.
Switzerland. Okay,
yeah.
Good. All
so
right.
actually, I got a pre-recorded talk.
Okay.
A very interesting movie that I'm about to show you.
So the title of your talk is "Key Player Problem in Complex Oscillator Networks." Okay.
Yep. So tell me in the chat if you cannot hear the sound, right?
Okay, go ahead. You can start.
Thanks.
It's pre-recorded, right there.
Okay. So hi everybody. My name is Melvin Tailu, and I'm currently a postdoc at the University of Applied Sciences of Western Switzerland, located in the middle of the Swiss Alps, as you can see in that picture that I took last summer. So first of all, let me thank the organizers of that session. I'm very glad to be part of this session to present you my work. So what I'm going to discuss now is this famous key player problem, in the particular case of coupled oscillators defined on complex networks. These results have been published in Science Advances. You get the reference there. You can check the article whenever you want, as it is available in open access on their website. So first, let me explain to you what I mean by this key player problem. So imagine that you have a complex system that is coupled. In the end, you have individual units that are coupled together by some complex network. That could be one of these 6, for example, complex networks. So obviously, there are two intuitive questions that one may ask actually about this system. Again, if you look at a particular network, which node in this particular network is the most fragile, in the sense that it might drive the system out of synchrony, for example, or away from its stationary or steady state. And this is what I'm going to discuss now, actually. How can we identify this most vulnerable node in a network just by looking actually at the coupling network? And then identify the most vulnerable component of a complex system just by looking at the coupling network. And of course, the same question is also, how should you connect your individual units together so that the overall system is rather robust to any external perturbation? And these are some actually investigations that we've made in that PRL some times ago. But I'm not going to discuss that today. If you're interested, you get the reference there. So the key player problem, okay? Let me just first quickly show you some numerical simulations that you can do. So what we have here is 2 times exactly the same complex system, but on the top, we'll apply a perturbation on that node in red, at the bottom on that other node in red, right? And we apply a perturbation between 0 and 1, and we just look at the trajectories of the degrees of freedom and of derivative, or time derivative of the degrees of freedom at each node. And you can see that the response of the system is quite different depending on which node actually you perturb, right? So now the question is, could we predict that behavior just by looking at the coupling network, right? Can we define some kind of centrality measure that would have allowed us to predict that behavior? Okay, and actually then, once we have these centrality measures to identify the most fragile nodes, we might go actually to larger networks. Actually, that might bring some more efficient methods to define the vulnerable components of a complex system rather than just doing numerical simulations, perturbing each node one by one, right? Okay, so this is the model that we considered. Actually, it's just a rather general model. In the end, it's just a second-order Kuamoto model. So at each node, you have some inertia and some damping parameters of the oscillators, and you have some natural frequency, right? And the oscillators are coupled together by this nonlinear coupling, where Bij is just the matrix elements of the adjacency matrix. And there you get the sign of the angle differences between connected nodes. And okay, so now we're going to take our complex system at some steady state, or synchronous state in the case of these Kuamoto oscillators. So if the coupling is strong enough, you will have these synchronous states. They might be different, many different actually stable fixed points when you have a complex network. But actually, from now on, let us just assume that we have some synchronous state. And what we're going to do now is just apply some perturbation in the natural frequencies, in the internal parameter of one oscillator, and try to quantify the response of the overall system to this change in the internal parameter of a single oscillator. So how can we quantify this excursion actually from the stationary state? So we can do it by means of these performance measures. In the end, you can just integrate the angle or degrees of freedom deviations from the steady state during the whole transient that the perturbation induced, right? This is just like an illustration of what we mean by these performance measures. In the end, it's directly related to red area. So the system is at a stationary state there. We turn on the perturbation, the system starts to move like this. And when we turn off the perturbation, given that the perturbation was small enough, the system will eventually return to its initial fixed point. And actually then, just by comparing the value of these performance measures, in the end, how big is this red area, we'll be able to tell whether the system in the end was robust to the perturbation with a rather small red area, or was rather fragile because you went quite far from the initial steady state and took quite a long time to get back to the initial fixed point. Okay, so now the idea would be to compute analytically these performance measures. And we can do it, given that the perturbation is small enough, we can linearize the system around a stable fixed point. So we have these natural frequencies that are now time dependent. It will make the degrees of freedom time dependent as well. There's this delta I there. If you plug these guys into the initial model, what you will get is this nice vectoral differential equation. And there you have this weighted Laplacian matrix, which is quite interesting matrix, as it depends both on the topology of the coupling network through the Bij's and on the steady state that you're considering through this theta I naught, right? And these theta I naught actually are dependent also on the initial natural frequencies P naught that you had, right? So now this is a linear system, so you can solve this differential equation for whatever kind of perturbation delta P of t you want. But we'll just create some particular delta P of t. Let me just quickly mention these different timescales that we have in this system. So we have some intrinsic timescales, which are just given by the individual elements, which is the ratio between inertia and damping parameters. And we have some network timescales, which are just the eigenvalues of this weighted Laplacian. And the third timescale is just actually the external perturbation that we're applying on the system. And now, depending on the ratio between these three timescales, we'll be in different regime for the response of the system. So in the end, to visit all these different timescales, we'll consider this noisy time-correlated perturbation. So in the end, we'll have just one node with some noise that is correlated in time with some characteristic correlation time tau 0. And then by just tuning this tau 0, we'll be able to visit the different timescale of the system. And we'll see actually that in the two asymptotic limit of very short and very long correlation time, we'll get interesting connection to some distance or some network quantities. Okay, so in the end, you can actually compute these performance measures analytically within this linear response theory. And for very short correlation time for the noise, when you have a perturbation of a single node k, this is what you get actually. And for very long correlation time, you get something quite similar, right? So in the end, this U alpha and this lambda alpha are just the eigenvectors and eigenvalues of this weighted Laplacian. So maybe let me just quickly mention that in the end, they all look quite similar, right? You always get the same kind of numerator and denominator, except for that one, where in the end, as the eigenvectors are normalized, this guy only depends on the number of nodes in the network. So actually, we could have stopped there because we have found some link between the performance measures and the eigenvectors and eigenvalues of the weighted Laplacian, which in some sense makes some connection between some dynamical behavior and the topology of the network. But actually, you can go one step further, because this guy can be re-expressed using this famous resistance distance. So this is distance that was introduced actually by Klein and Randich in their seminal paper there. It's defined out of the pseudo-inverse of the weighted Laplacian, and can be written in this very convenient way using eigenvectors and eigenvalues of the weighted Laplacian. And it has this very intuitive meaning that omega ij is just the effective resistance in a network of resistors, where on each edge you have a resistor with a resistance given by the inverse of the edge weight of the original network that you're considering. And actually, you can generalize this distance to these new quantities there, omega I, j, p, where you just have lambda alpha to the power p now, which would correspond to the Laplacian to the power p, right? Like some kind of new definition of this quantity to the pth power of the Laplacian. Of course, whenever you get this quantity that relates, that then gives some connection between node I and j, you can define these Kirchhoff indices, which is just the sum of this quantity, this omega ij, over the whole over all pairs of nodes, and it can be simply written as a sum of the eigenvalues to the power minus p. And you can also define, so in the end, this is a like global quantity that defines the network as a whole, and you can define some centralities, which has, this is just like the usual definition of a closest centrality. So you take one node k, and you will calculate the mean value of omega from k to all the other nodes in the network, take the inverse of this quantity. If it's large, it means that the node is quite close to all the other nodes with respect to this omega. And if it's quite small, it means that the node is rather peripheral according to that quantity. And you can write it in this very convenient way using eigenvectors and eigenvalues of the weighted Laplacian and the Kirchhoff indices. So now you can simply write our performance measure using these centralities and these Kirchhoff indices, right? And you can see that in all cases, except P2 in the short correlation time, that depends only on the number of nodes, you can always rewrite this performance measure as function of this centrality matrix, right? And also this overall network descriptor of these Kirchhoff indices. So in the end, relates some dynamical behavior of the system, the excursion of the system to some centralities, depending on if you're interested in the degrees of freedom, on the derivative of the degrees of freedom, or on the short or long correlation time of the perturbation, right? So now we can go back to the initial illustration that I showed you. So actually, the centrality of that node was smaller than the one at the bottom. And if we have a look at what we found there, actually, the performance measure is proportional to the inverse of the centrality, which means that the guy with the small centrality will have the largest response. And that's exactly what we get there, right? The response is quite larger for the guy at the top compared to the one at the bottom that has a larger centrality. Okay, so then we can also test our theory on larger networks. We used like a huge network of almost 4,000 nodes, which is just a model of the European power network. And so different colors correspond to different correlation time of the noise. And you can see that on all time scale for the correlation time, our theory works well for both P1 and P2. But we have these two cases of the red and blue one, which are just very short and very long correlation time. And you can see that the performance measures are very well correlated with the centrality with the centralities that we defined. And these are the maps of the European network actually that we used. So these are the map for C1 and C2. So the nodes in blue will give you rather small performance measure P1 for degrees of freedom. And when you're peripheral, like in Sicily or maybe in the Balkans there, you will get a rather large response for the degrees of freedom. But then if you're interested in rather in the time derivative of the degrees of freedom, you will have to look at that map. And then you can see that the nodes that were the most fragile according to C1 are not necessarily the same for C2, right? It really depends on which correlation time you're interested in, like long or short correlation time. And if you're interested in degrees of freedom or the time derivative of the degrees of freedom. Okay, so let me quickly conclude. So in the end, relate the local vulnerabilities of these complex oscillator networks to these new centralities, C1 and C2. And yeah, the order of this centrality depends on which performance measure you're interested in and on the correlation time of the perturbation. So, I mean, generally, we found that Indian resistance distance is the right quantity to look at if you want to quantify the response of coupled oscillators. And okay, as I told you at the beginning, if you're interested in the global robustness of a system, just comparing different networks, you can have a look at what we did in that PRL in 2018. We also have this PRE where we compare actually global robustness versus local vulnerabilities, which is quite interesting trade-off between centralities and Kirchhoff indices. And if you want some more details about this, what I just presented, I'm giving a talk, rather a slightly longer talk on, at the satellite conference, Complexity in Energy Systems tomorrow at 2:30. So thanks for your attention, and I'm looking forward to your questions.
Okay, thank you very much. Okay.
Thank you.
Any question? You have any question? Okay, I have a question. If nobody else asks, then I can use my privilege as a chairman. Okay, now what happens if, now in this case, you have one network, right? What happens if you have one network controlling the other one, like in this well-known case of Italy and the collapse of the electric grid? I mean, can you handle cases like that? And as far as I know, Havlin's work, I mean, and the other people, this leads, if I remember correctly, to a first order, first transition now, or something of that type.
Yep. Okay, that's a very interesting question, and that's definitely one of the extension that we would also want to investigate a bit. In the end, we only considered like, so to say, single networks, where with some kind of single dynamics without any like interdependent networks. So, yep, in the end, we should generalize these centralities to these interdependent networks, I guess. But honestly, I don't have any intuition now to give you about what we would get. In the end, I would say that if you want to apply some control, like add another layer of a network that would just control the first one. Maybe now with our centralities, we could actually just find which node should be controlled or should be secure in order to have a network that is a bit more resilient. But other than that, yeah, we should look into that a bit deeper, I would say. Yeah.
Okay. Does Vasilis Vasios wants to ask something?
If I may, it's on the line of these segregation networks.
Okay.
I'm aware of certain papers and work that has been done on segregating networks, like in neurons and all that, where the whole power is getting localized in one region. I mean, really localized in the other one. So, and then you have this, as George said, the phase transitions. But the question I would like to ask is, could there be the boundary could influence this, the response of the function? The boundary meaning in the end of the network, there must be some network, some privilege. Yes. Okay.
Yeah, okay. That's also a very good point, actually, because the network that I show you of the European power network actually is only like the high voltage transmission network. In India, whenever you have a node, it's most of the time not the end of the system. Usually you get a low level of voltages with some distribution network. So I have to say that it's something that is not taken into account in these like swing equations or second order Quantifying model. And actually, the thing is that when you have these high voltage power networks, we have this constant amplitude of the voltages, which makes the things a bit easier, I would say, because you will only have this second order Quantifying model with constant edge weights in the end. And yeah, when we have these distribution networks, sometimes you have the voltage levels that are actually fluctuating in time, that are not always constant, and yeah, that brings some interesting dynamics for sure. But yeah, the equation then is also a bit more complicated, I would say. So honestly, we never really looked into these extensions. I guess numerically there's for sure interesting things to do about that, because in the end it will also relate to these interdependent networks, I would say, or networks of networks, right? Yeah, thanks a lot. Yeah.
Okay, thank you very much.
Thank you.
Okay, our next speaker is Julia Cantisan.
Yes. Hello.
Hi, Julia.
Hi.
Where are you? Where are you right now?
Spain.
Ah, you're in Spain. Okay.
Yes.
Where in Spain?
Madrid. Madrid.
Madrid. Okay. ¿Cómo está el tiempo en Madrid?
It's very good here.
Good. All right. So the key, the title of the talk is Transit Dynamics, Dynamical Systems Subjected to Parameter Drift.
Yeah, that's
Okay.
it. So I have also my pre-recorded presentation.
Okay.
So, here goes. Hi everyone, this is Julia from the Universidad de Goncalves in Madrid, Spain. I'm going to talk about the transient dynamics in systems that suffer.
I cannot hear you. Julia, I don't know about other people, but I cannot hear you. You are muted. Julia, you are muted.
Hi everyone, this is Julia from the Universidad de Juan Carlos in Madrid, Spain. I'm going to talk about the transient dynamics in systems that suffer a parameter drift. So first of all, why these kind of systems? Well, a vast variety of systems are not static over time, in the sense that they cannot be modeled by the same set of equations or parameters as time passes. When a parameter varies with time, we say that there is a parameter drift. This can be caused by external factors, as the increase in greenhouse gases in the context of climate dynamics. And also this can be caused by internal factors, that is, by the nature of the system itself, as in the case of some engineering systems that wear out. Even some systems are modified on purpose by experimentalists. So when a parameter drifts at small but non-negligible rates, the time dependence of the parameter represents a small perturbation. Thus, the associated frozen-in system, that is, the system with fixed parameters, provides a useful information about the non-autonomous system. A vital part of the analysis of a nonlinear system consists on the computation of bifurcation diagrams that depict the steady state of the frozen-in system for different and fixed values of the parameter. Here we have the bifurcation diagram of the logistic map. What we can see is that in this range over here, the system has a different dynamic from the one over here once we pass the bifurcation value. Now, if our parameter varies with time, we may cross this bifurcation value. This type of bifurcations that are crossed due to the time dependence of one of the parameters are called dynamic bifurcations. Previous work on dynamic bifurcation has been restrained to systems with regular attractors. But we studied this phenomenon for a chaotic system and also for a time-delayed oscillator. Here I will talk about the Lorentz system, and afterwards I will leave the reference about the case of the time-delayed oscillator. So let's get started. Here we have the Lorentz system. We fix sigma and beta to the classical parameter values, and we depict here the bifurcation diagram with respect to R. we are going to focus on what happens before and after the heteroclinic bifurcation at R2406. Before this value, you can see here two trajectories. There are two fixed points. The stars correspond to the initial conditions, and the trajectories end in the red attractor or the blue attractor. After the bifurcation takes place, you can see here three trajectories. A chaotic attractor appears, and the three attractors coexist: the red one, the blue one, and the chaotic attractor. Here I show the basins of attraction before and past the heteroclinic bifurcation for a sphere of initial conditions. In red and blue, you can see the initial conditions that end in the fixed points, and in yellow you have the ones that end in the chaotic attractor. So this is the picture for the frozen in Lorentz system. Now we're going to let the parameter vary between those two scenarios. We make it vary linearly with time with a certain change rate that we call epsilon. So first, R is fixed to 24.5 past the heteroclinic bifurcation so that the chaotic attractor is stable. Then R decreases slowly with time until T2. And what do we see? Well, this is a trajectory for a concrete value of epsilon. In the secondary x-axis, we show how the parameter R decreases with time. If you remember, the chaotic attractor lost stability at 2406, which is over here. This is for the frozen in Lorentz system. However, here we have the parameter is drifting. So we see that the motion is chaotic up until a value over here where the line turns blue. That is past this one. So the transition from one regime to another appears for a value that we call R critical, and that is different from the bifurcation value. And this is for one initial condition. What happens for other initial conditions? Well, we computed 10,000 trajectories studied on the previously shown sphere, and it turns out that they don't tip at the same time. This is one of the differences from the study of dynamic bifurcations in systems with regular attractors. When a chaotic attractor is involved, we have a distribution of times and values of the parameter at which the system tips. In this case, we can see that the median value is around 23. Okay, so we've seen that different trajectories tip at different times, but do they tip to different attractors? Yes, they do. On the left, we can see the basin for R equal 24.5, where the yellow regions correspond to the initial conditions that end in the chaotic attractor. As you can see, these regions disappear when R is varied, because we cross R critical. Due to the symmetry, half of the trajectory is tipped to the blue fixed point, as seen in the previous slide, and the other half tipped to the red one. This type of basin is called scenario-dependent basin because it depends on the values of T1, T2, epsilon, etc. And due to the passage through the chaotic attractor, this basin does not show any pattern, and both basins, the red and the blue one, are completely intermingled. You can think it this way. The final destination of the trajectories is related to the precise moment that the trajectory is caught wandering in the chaotic attractor when the parameter shift starts, rather than to the initial condition. In other words, predictability of individual trajectories is lost because the passage through the chaotic attractor induces fractal basins of attraction, and this is what we call random tipping. Also, due to the presence of the chaotic attractor, The spatial distribution of R critical in this sphere of initial conditions presents no pattern, and the initial conditions that lead to longer and shorter metastable states are completely intermingled. We may say that the chaotic attractor acts as a memory loss agent. Finally, we may ask ourselves if the median value of R critical depends on the parameter change rate epsilon. Well, it follows a power law, so that when we move faster, the transition on average occurs at values farther from the bifurcation value. This is usually referred as the delay effect. We have also represented here the frozen-in case, which is for epsilon equals to 0, where the transition occurred at the bifurcation value 24.06. So, as you can see, when the change rate is increased, the value for the transition moves away from the bifurcation value. Also, it is interesting to see this in terms of time. If we consider that the transient dynamics is what happens before the system tips to either of the final attractors, we can talk about transient chaos. We represented here the normalized number of trajectories that remain in the chaotic attractor for a certain value of time. So, for example, for the blue one, you can see that up until this value, all of the trajectories remain in the chaotic attractor. Then, as time passes by, some trajectories go to one of the red or the blue attractors, up until this value here, where all of the trajectories have reached their final states. So, as we can see, when we go faster, the transient time, that is the time before the system reaches its final state, is shorter. However, if the parameter varies very slowly, trajectories tip next to the bifurcation value, but the transient lasts for long periods of time. Before I finish, let me make a quick sum up of my presentation. I've shown you that in systems that suffer a parameter drift, if this parameter crosses a bifurcation, the change on the dynamics is not immediate. On the contrary, there is a delay effect that provokes that for faster rates, the transition on average takes place at further values from the bifurcation. In terms of time, if the parameter is varying very slowly, the change on the dynamics may not be noticed until long after the parameter drift has started. Also, I've shown that the chaotic attractor acts as a memory loss agent. Due to the passage through the chaotic attractor, the basing of attraction becomes fractal, and predictability of individual trajectories is lost. With these results, I published 2 papers along with my 2 PhD supervisors, Jesus Seoane and Miguel Ángel San Juan. In the first one, you can see, we can find in more detail the analysis of the Lorentz system that I have just explained. And in the second one, you can find the analysis for the time-delayed Duffing oscillator, where the parameter that drifts is the time delay itself, and some particular results are found. Thank you very much for listening, and thank you to the organizers for this amazing conference. Now, if you have any questions, I would be happy to answer them.
Okay, Julia, thank you very much.
Thank you.
Okay, I think Vasilis has a question.
Mm-hmm.
So, sorry to monopolize the questions, but this is fantastic work. Congratulations. This is a statement, not a question. My question is whether or not this has relevance to what they call chaotic itineracy, where you have ruins of attractors when the parameter is going from one value to the other. As you say, they have discovered that's the work of Ikeda, that has discovered the so-called ruins of attractors. Did you ever encounter such a phenomenon there, like an attractor that remains there, like a ruin?
Mhm. No, I haven't, but I will.
Okay. Is there any other question for Julia or Julia? Any other question? Now, let me ask you something. The change in the parameter you do slowly, right? It's adiabatic. Is this correct?
Yes.
What happens in the other extreme if I do it very fast? If I do a sudden change?
Well, if you go very fast, it's more complicated because you find the next bifurcation too early. So you can't really see what happens when the chaotic attractor disappears, because quickly you find out that the fixed points disappear too. So it's not exactly what we were looking for.
Okay. All right. Okay, thank you very much.
There is a question in the chat, if you wanna read it.
I'm sorry, I didn't check the chat.
Oh, okay. Yeah. What is the specific numerical criterion you use to determine whether the trajectory has reached, okay, the red or blue attractor? Yes, the criterion is that you enter a sphere of radius, I think it was 0.001, or I think it was this value. And when it enters this sphere center at the fixed points, we say that it has reached the final attractor.
Is there another one? Okay, all right. Thank you very much. Okay, thank you. And we move on to the next speaker, who is Dalton Oliveira.
Hi.
Hi.
Hi. Hello.
Hi. Where are you? Where are you right now?
Yes. My internet, my connection internet is bad. It's bad. Hi.
So are you going to present the talk, or are you?
Okay. I'll present the talk. Hello, my name is Dalton Oliveira. I am student PhD and São José dos Campos, Brazil, Institute of Aeronautical Technology. Chaotic transient and distributed in half-square dynamo model. Chaotic transient are a common phenomenon in fluids, and the plasmas Benigni usually associated with the turbulence, really initial erratic fluids converge to laminate state. Chaotic transient are known to presence of the non-attraction chaotic series in the phased space. In space and the astrophysical plasmas, chaotic transients related to chaotic shadow have been observed in numerical simulation of the alpha-EVN waves, magneto-hydrodynamics, dynamo, and the accretion disks. Many astrophysical systems such as planets, stars, and the galaxy show variable magnetic field. A larger scale dynamo is responsible for the generation and the maintenance of a larger scale magnetic cycle in astrophysical body. The plasma in such bodies usually display differential rotation while the angular velocity is not but uniform but varies according to the latitude. A large-scale dynamo is responsible for the generation and the maintenance for larger-scale magnetic field and the cycles in our astrophysical bodies. The plasmas in such bodies usually display differential rotation, where the angular velocity is not uniform but varies according to the latitude, depending on the relative importance of the differential rotation, which gives rise to the so-called omega effect, and the helical convection, which gives rise to the so-called alpha effect. To large-scale dynamos is characterized as alpha square or alpha omega dynamo. When the differential rotation is significant, the dynamo is of alpha omega type. The solar and the galactic dynamos are reduced of alpha omega type. Moreover, there can be some objects in which the rotation is very uniform, like the wreath and the dynamo is of alpha squared type. In rapidly rotating star, the differential rotation is highly quotient, while the alpha effect remains strong and thus the dynamo is expected to be alpha squared type. The motivation of the present study explores the origin of chaotic transient nerve to onset of the alpha squared dynamo in the presence of steroids. For this, we consider for cycle 3D MEAGD model of isothermal compressible fluid right hard drive being a radical function force function. The advantage of including an external drive is that it can vary the notch edits or explore the dynamo transition. Transition to dynamo is shown to be to a direct blowout bifurcation, which takes place when a smooth invariant manifold with a chaotic attractor loss transversal stability. Blowout bifurcation can be of the two types, direct, characterized by B-stability, or non-direct, characterized by on-off intermittency. The model of simulation we adopted to model of alpha squared dynamic plot. The fluid is assumed to be isothermal and compressible, with constant solid speed, constant dynamical viscosity, constant magnetic diffusivity, and constant permeability. The governing equation are equation continuity, equation momentum, equation induction. Equation induction. The kinetic energy is injected in the system by a forcing function, which is defined by the operator, this guy phi. This rate complex force function has been employed in several previous works for being able to generate turbulent statistics, even for moderate reduced number, and for us it's interesting because it allows us to choose the level of illicit added to the flow. An important element for the generation of large-scale dynamos. Numerical simulation. First, we must choose the gradient resolution for the numerical simulation of equation continuity, momentum, and equation induction. The figure shows a comparison of the time series of the root mean square of the magnetic and velocity field in log linear x for the simulation. Initially, the seed magnetic field is to work to impact the velocity field, but the velocity field has a strong impact on the induction equation, causing an exponential growth of the magnetic energy during the initial phase of the dynamo. The figure represents the spectrum of the kinetic energy and magnetic energy at times for sigma equal 1. And the figure represents intensity of plots of magnetic field and velocity field for sigma 1. The bifurcation diagram shows the time average BAMS as the function of sigma. The onset of the dynamo action is shown in figure, which represents the bifurcation diagram as a function of the sigma of the time average root mean square magnetic field. For rate value of sigma, a weak seed magnetic field is Z has initial condition. The initial transient is discarded and then times average of magnetic field are plotted. The magnetic energy of the attractor is 0 VB. Note that of the critical transition, the hydrodynamic attractor lost stability and small amplitude magnetic perturbation are sufficient to drive the system towards the hydromagnetic attractor. The time series of BMS nearly the critical transition the dynamo action on hydrodynamic attractor, attractor hydromagnetic. Hysteresis and chaotic transient. Motivated by Karmakar et al., research for hysteresis is the dynamo system. Actually, the work has imposed uniformly large-scale shear flow that is absent in all simulation. We still managed to define the hysteresis in our alpha square dynamo model. The transition the hydromagnetic attractor take place sigma equals sigma critical, where when the sigma magnetic field is amplified. Due the seed field is decay to 0, has the solution approach hydrodynamic attractor. However, if only takes as initial condition a state which high energy magnetic field is may not decay the hydrodynamic attractor. I show figure here the initial condition is state taken for hydromagnetic attractor at sigma equals 0.3 when the control parameter is reduced to sigma equals 0.2. The solution remains in the hydromagnetic attractor if the magnetic resonance still follows the upper branch figure. That is signature of hysteresis is the saturation of magnetic field amplitude dependent of the previous stored parameter control. The figure represents a time series of magnetic fields exhibiting hydromagnetic chaotic transients. The transients. The figure represents space-time evolution of the horizontal variation bits as function of z and time. Trajectory the initial condition on invariant set in the space for hydromagnetic attractor. The figure represents scale law of the hydromagnetic chaotic transient as a function for distance to the boundary crisis values. As figure illustrates the average duration of the chaotic transients decrease with decrease sigma. This observation suggests that the destabilization of the hydromagnetic chaotic attractor. A chaotic cell is then left in place of the chaotic attractor and it shows garbage et al. The average duration, the tau of the chaotic transient near boundary crisis decay with the distance from the crisis parameter. Following the scale law, hysteresis and the chaotic transit, schematic bifurcation diagram has a function of sigma. Solid lines in the indicate attract solution, and the dashed line indicate non-attract solution, responsible for chaotic transients. The red line represents hydrodynamic state, and the broken black lines represent hydromagnetic chaotic state. Conclusion. We have found a transition to dynamo statistic blowout bifurcation in direct numeric simulation of MAG alpha square dynamo model. The work Kinol is the first time where the statistic blowout bifurcation is observed in alpha square dynamo model. This work illustrates the importance of chaotic transients in revealing the complex dynamical transition present in turbulent flows. The hydrodynamic chaotic attribute in the upstream branch destroyed in the boundary crease. Actually, we have not formally characterized the blowout bifurcation and the boundary crease. The behavior of the chaotic transient generated by all transition strong suggests that is not the case. This work illustrates the importance of chaotic transients in revealing the complex dynamical transition in turbulent flow. Thank you very much.
Thank you. Thank you. I think Vasios has a question.
Hi. My internet connection is bad, very bad. White chat, please.
So anyways, we heard your presentation. It's okay. And Vasios has a question or not? But is there a question?
Not on my part.
Okay. Is there any other question? Is there any other question? Okay. Thank you very much. Okay. Thank you very much. And we also have, there's a chat. Let me see in the chat something. Okay. So this is not, all right. Okay. Thank you very much, Dalton. And we move on to the last talk by Kamia Tavakoli.
Hi.
Kamiar, hi Kamiar, where are you right
I'm
now?
in Canada.
All right. Is it cold in Canada or warm? Is it
Yes,
snowing?
yes, it's really cool. The winter has begun.
Okay, good. Winter is fine because after winter we have spring and then we have summer. So
yeah.
All right. So your talk is about complexity and entropy reduction in systems with multiple delays. Please.
Yes. Sorry, I have to fix this.
It's okay.
Yes, I have to share it again. Hello, everyone. Thanks for having me. I'm Kamia. I'm a PhD student at the University of Ottawa under supervision of Prof. Andre Longton. It's my pleasure to participate in this fantastic conference. What I would like to talk about is the complexity and entropy reduction in systems with multiple delays. So first, I'm going to talk about the effect of multiple delays on the dynamics of the semiconductor laser with optical feedback. In the experimental setup of semiconductor laser with optical feedback, an external reflective device is used to induce dynamical instabilities. So depending on the reflectivity of the external device and its distance to the semiconductor lasers, different dynamical behaviors can be observed. The rich dynamical properties of the semiconductor lasers with optical feedback makes them enabled to be exploited in wide ranges of applications, such as reservoir computing or random bit generator devices. So each of these devices demands different degree of complexity. So we thought maybe changing the number of delays may help us to tune the degree of complexity in this system. And we have found out sometimes more delays leads to higher complexity and sometimes results in much more simplicity in the dynamics. So in order to better understand the dependency of the complexity to the number of delays, we estimated the dynamical invariants such as Lyapunov exponents. Calculation of the Lyapunov exponents help us to obtain more useful information about the dynamical properties of the system. So the dynamics of the semiconductor laser with optical feedback can be modeled using Lang-Kobayashi equations, in which E shows the complex electric field and N shows the carrier density. Without the feedback term, the dynamics follows the relaxation oscillation dynamics, but with the proper choice of the feedback strength and time delay, oscillatory and chaotic behavior can be observed as well. So we know that single delay can induce instability in the dynamics, but what would happen if there are many delays in the system? So in an experimental setup suggested by Zhu et al. In 2017, a fiber random gratings was used as an external device. A fiber random gratings consists of many segments that within each segment, a scattering center is located randomly. So in this case, the dynamics is affected by many delayed states. They showed that using fiber random gratings leads to higher complexity in the dynamics. This is not what we usually expect from systems with many delays, as it is shown for many models that when there exists an infinite number of delays and the width of the distribution of the delays is large enough, a simpler dynamics can be observed. So we began to study the dynamics of the Lang-Kobayashi models with multiple delays. We picked delays in a way that the average of the delays remained approximately fixed upon adding more delays. So in the first column of the right figure, the attractor plots of the intensity versus carrier are shown. So the intensity is the squared modulus of the complex electric field, and the autocorrelation function of the intensity is shown in the middle column, and the third column shows the intensity time series for different number of delays. So in the case of single delay, we can easily detect the time delay that is used in the equation. So in order to increase the complexity, this time delay signature has to be suppressed. As the number of delays increases to 20, we can see that the dynamics becomes much more complicated in a way that we no longer can see any signature around the time delays. And also we can see that the relaxation oscillation time becomes more pronounced. When we increase the number of delays to 160, the dynamics becomes much more simplified in a way that the attractor shows torus behavior, and the dynamics is mainly governed by two time scales, which are the relaxation oscillation time and the average of the time delays. Further increase of the number of delays to 180 results in a simple oscillatory dynamics with the period of the relaxation oscillation time. For a very large number of delays, for example, 1000 delays, a stable fixed point behavior can be observed in the attractor. In order to characterize the complexity of this multi-delayed system, for different number of delays and different feedback strength, we measured the maximum of the autocorrelation function of the intensity around the average of the time delays. So in this color plot, the red region corresponds to the low complexity regime, and blue regions corresponds to the regimes that shows hyperchaotic dynamics with high complexity. So for fixed feedback strength, in most cases, as we increase the number of delays, the complexity first increases, and as we increase the number of delays more, we can see that the complexity decreases, and eventually in the limits of the large number of delays, the complexity collapses into the low complexity regime. And for fixed number of delays also, we can see that as there are more delays in the system, a stronger feedback coefficient is needed to enter to the chaotic regime. So this reduction of complexity due to the existence of more delays in the system is similar to the case of the distributed delay differential equations when the width of the distribution of delays is increased. So we were wondering what would be the dynamical properties of the semiconductor laser if it described in the form of the distributed delay differential equations. So in this case, we assumed the delays have a uniform distribution and they are not picked randomly anymore. And many delayed states are affecting the dynamics of the current states, and each of them has an equal weight. So in the right figure, we can see the simplification of the dynamics due to the increasing the width of the kernel. For example, we can see that the chaotic attractor has become a torus as we increase the width of the kernel. So in this color plot, also we can see that for different feedback coefficient and different width of the kernel, after a specific limit, we no longer can see chaotic behavior anymore, and it doesn't matter anymore that what feedback strength that we used in the equations, as the red regions occupies the whole space. And it's interesting that both the distributed Lang-Kobayashi model with delays and the Lang-Kobayashi model with multiple discrete delays that show that after a specific limit, their dynamics is simplified a lot. So next, we calculated the degree of unpredictability in the system of Lang-Kobayashi model with multiple discrete delays. So we measured the unpredictability degree through the calculation of the Kolmogorov-Sinai entropy, which is the sum of the positive Lyapunov exponents. In order to calculate the Lyapunov exponents, we assume that there are n+1 points between each two neighboring delays, and the dynamical state corresponds to these points is described by these equations. And from the linearized form of these equations, we can calculate the Lyapunov exponents. So in this figure, the left panel, we assume that the feedback strengths are fixed and we change the number of delays. So for weak feedback coefficient, we can see that the Kolmogorov-Sinai entropy starts to decrease from the beginning. But for moderate or strong feedback coefficient, the Kolmogorov-Sinai entropy first increases, and in the limits of larger number of delays, the unpredictability decreases in the system. So in the right panel, we assume that the number of delays is fixed and we change the feedback strength. And we can see that for any given number of delays, as we increase the feedback strength, the Kolmogorov-Sinai entropy first increases, and for a very strong feedback coefficient, the Kolmogorov-Sinai entropy decreases. So the location of the peak of the maximum unpredictability in the system depends on the number of delays that we have in the system. So we were wondering if this reduction of complexity could also be seen in other nonlinear time-delayed systems, such as Mac-Glass model, which is a biological model for blood cell production. So in the bifurcation diagram, we can see that as we are increasing the number of delays, a sudden periodic window appears, and then it followed by a small chaotic windows, and then again followed by larger periodic windows. And at some point, it experiences an inverse period doubling bifurcation, and in the limits of the large number of delays, it becomes a stable fixed point. So this reduction of the complexity can be better seen in the plots of the permutation entropy for different number of delays. That we can see that even in the chaotic regime, the entropy generally decreases as we increase the number of delays, and then suddenly drops, and we call this a complexity collapse. And we can see these bumps, which are corresponds to the small chaotic windows. And we can see eventually in the limits of the large number of delays, the entropy becomes 0. So in order to sum up, we have seen the paradoxical effect of multiple delays on the dynamics of the Lang-Kobayashi model with multiple delays. We've seen that in most cases, increasing delays first increases the complexity, and for a larger number of delays, this complexity collapses into the low complexity regime. And also we saw that for both discrete and distributed delayed differential equations for line conversion model, after a specific limit, they both show much more simplified dynamics. Also, it appears to us that the simplification of the dynamics due to the existence of many delays in the system is the fundamental property of the most delayed differential equations. And I'm going to stop here. Thank you very much for your time.
Okay. Thank you very much. Okay. Is there any question? Any question? I'm wondering, there's a chat. Really, I don't know if this refers to this or not. Maybe it's before. Okay. Are there any? These are theoretical results. Is there anything experimental in this direction?
It is not shown for semiconductor lasers, but there are some results regarding the simplification of the dynamics in the SPS lasers, but for semiconductor lasers it is not shown yet.
Mm-hmm. But do you think these effects can be observed experimentally? Is it possible to observe them?
I think so, yeah.
Okay.
Can I,
yes, please.
Can I ask a question? It's mostly from my education, if you please. Is there a connection between time delay systems and fractional derivatives? Because fractional derivatives also take into account a certain time around, like they have a memory around the original state. Do you know any connection with that? I would be glad if you...
I'm not aware of that, but I think so. There is a connection between them, actually.
Okay, thank you.
Yeah.
Okay. I don't know if there's any other question. Maybe not. Okay. End of the session. I think it was quite interesting. We learned a number of new things, at least I did. Thank you very much for being here and participating. And I wish everybody to be in good health. And hopefully next conference will be closer to one to the other. Okay, thank you very much. Okay, this is the end of the session. Okay, take care. Bye-bye.